right, it's time. Everybody's excited. We're here for the final presentations of the 2019 Summer Institute in Computational Social Science Week 2 group projects. So for everybody in the room and on Blue Jeans who is not quite as familiar with everybody here and what we've been doing, the first week we all got together to learn about new and exciting methods in computational social science, anything from collecting digital trace data to text analysis, automating all of this. And we've kind of dabbled in everything. The second week was really meant to do some, well, how I like to call it, thick research. Okay, that was trying to be a joke from a German. And so this presentation today, we're really going to go deeper into what we've learned during the first week. And we have 6 groups who are going to present what they did during this past week. And we're very excited. And Emily is going to be announcing our first group. And the way this is going to go, we're always going to have 15 minutes of presentations, maximum, with a 10-minute Q&A. And we'll have questions on Blue Jeans. We have questions in the room. We'll have then people maybe come and go during 5 minutes and set up for the next presentation. And now everybody have fun, enjoy, and be just as excited as the last 2 weeks have been.
Thanks, Antia. I'm Emily. I'm one of the TAs along with Marcus. We're going to be the ones introducing the presentations. Before we started, we just wanted to say how amazing it's been to work with you guys for the last week or so on your projects. It's been a lot of fun. You guys have asked a lot of good questions and really pushed us to dig deep into our technical skills. So we've had a really good time and are looking forward to everything that you have to share with us today. So first up, we've got the team that is presenting on utilizing synthetic populations to estimate student preference for living close to home during college and college distance in North Carolina. We ask you guys to come up and also introduce yourselves and where you're where you work or are from before you start the presentation. Thanks.
Nice idea from the start. Sure. This isn't working. So I think you just press it. Yeah. Hello? All right. Thank you. All right, good start. My name is Becca Merrill. I'm a recent graduate from UNC Chapel Hill in the School of Education. I focus on policy, leadership, and school improvement. And I'm going to be working in Portland, Oregon at a place called Education Northwest, which I'm finding is kind of a mini RTI out in the Northwest, but it focuses specifically on education and it works on evaluation for clients and especially trying to solve education problems in that region.
Hi, I'm Tara Weatherholt, and I am a education analyst in the International Education Division of IDG here at RTI, and I do mostly monitoring and evaluation and research on the early childhood development team, and primarily in developing countries.
Hi, I'm Derek Ramirez. I'm a data scientist, statistical analyst here at RTI inside of Sphere. I'm in the supergroup doing prevention science, and I work under the larger center, social determinants, with Philip Graham.
And I'm Nestor Ramirez. I'm a research education analyst here at RTI as well, in the Center for Education Survey Design and Analysis. That's housed in EWD. And I work on post-secondary surveys for the Department of Ed.
Yeah. Hi, everyone. Can I see a show of hands? Who, for everyone here, how important was it for you to live close to home when you went to college? Can I see a show of hands if it was important for you? Okay. And then how many of you actually lived close to home or lived close to a college? Your home was close to a college. Okay, great. So those are the 2 questions that we decided to examine using computational science methods. this. Right. Okay, so our research questions. The first thing that we wanted to do in our project was to determine if we could predict North Carolina high school student preference for living close to home during college. And we'll talk about methodology a little bit later, but we wanted to use synthetic population data set that's housed here at RTI in order to do so. The next question we wanted to examine was if there were geographic patterns across North Carolina in the student preference for living close to home. So what did that look like across the state? And then the final question was, do students with a strong preference for living close to home have nearby college options?
So to examine these questions, we actually had to rely on quite a bit of data sources. So we used 4. The first involved the High School Longitudinal Study of 2009, known as HSLS. We used the public use file that NCES provides, which is the National Center for Education Statistics, that had variables that we wanted to predict, including whether or not a student indicated that they preferred to live close to home when they were choosing a college. In addition, we used RTI synthetic population data file from 2010 and the PUMS file, which merges together to create a picture of every member, essentially every household and the members of those households within the United States, but also allows you to use different variables and characteristics that would normally be restricted since they would be identifiable. But since it's a synthetic population, you can mess with it without identifying specific individuals. And then the last data source we used was IPEDS, which provides essentially a list of all colleges in the United States that rely on or that accept Title IV funding. And that file has longitude and latitude for these institutions. So we were basically able to combine these 4 data sources to get a picture of not just where these students live, but also the location of the colleges near them.
So using the synthetic population that RTI has created, we took that and then merged it with the PUMS data to get additional information on all 9.3 million people, synthetic people that are in North Carolina. And then, as Nestor mentioned, we used a model, supervised machine learning, to map certain characteristics from the HSLS file onto the synthetic population. So we have our population data sets. We use supervised machine learning because the educational aspiration variable that we were looking at had 8 categories. And the preference for being close to home had 3 categories. So supervised machine learning was the perfect data set for us, or just the perfect methodology for us. And then, again, as Nestor mentioned, we had the IPEDS data that gave us all of the colleges in North Carolina. And because of the synthetic population, we knew where everyone was. So we were able to do a distance matrix where we took every student in North Carolina and then mapped them to all, I want to say 195? 154 colleges in North Carolina. So we had a large distance matrix that told us how far each person was and which one was their closest college. So the steps, as we mentioned earlier, we defined the questions, the research questions that we were interested in. Then we had to identify the relevant variables inside the data sets. The great thing about the synthetic population, because we developed it, we had a lot of data about each individual. Our main restriction was finding variables inside of the HSLS data set that matched so that we could run our trained machine learning model on the synthetic population. Once we identified those variables, we cleaned the data set, which for me, I think is the fun part. I'm sure it's not fun for everyone. So we cleaned HSLS. We made sure that our variables matched inside of the synthetic population. After that, we computed the prediction model, which I'll go into in a little bit more detail in a moment. Calculated the distance matrix in order to do our maps, and then created the maps themselves.
So as I'm sure every other group will mention, the bulk of our work involved cleaning the data files and making sure that everything looked the way it was supposed to for us to run our analyses. So we put up a chunk of code that you don't have to actually parse out, but I'll kind of talk through essentially what our process was. So we started off basically having to like Derek said, figure out what variables were in each data set that we could model off of, and then get them into a point where both the values for each of these variables matched up, and that the data set, like for HSLS, that we were only using the amount of observations that we needed. So like as an example, we were using I'm not going to dive too much into like the weeds of HSLS or anything, but the variables we were using spanned both the base year and the first follow-up. So we needed to essentially truncate the sample file in order to only account for individuals who responded to both surveys, right? And then from there, we found out how old, like the age range was for those students in the public use file, then went over to the synthetic population and broke that down based on the age range. Did some more coding where we got to see what the highest education was in the household, yada, yada, yada. And then we eventually ended up with a file, right? That took quite a bit of work. But yeah, and then from there, we were able to train the model, which Eric's going to talk about, onto HSLS and then port it over to the synthpop file. Cool.
Thank you. So again, I'm not going to get into too much of the weeds for training the machine learning model. But as I said, because we are dealing with educational aspirations that had 8 categories, and then we had the preference for being close to home, that was 3 categories. We wanted people to be in a specific one, so we couldn't do a regression. Like there's not a even distance among the categories for either one of these. And because it wasn't 2 categories, we couldn't do a logistic regression. So we put the data into R and ran machine learning models. Due to time constraints, we didn't go through the entire gambit of machine learning models that we could have, but we used some of the greatest ones like k-nearest neighbors, classification and regression trees. We did a neural network, and then we did a multinomial log linear network. The great thing about machine learning nowadays is, especially in R, it's so easy to use. So we use a library called Carrot. It has a standardized interface for any machine learning model. And essentially, when you want to run a different model, you just put in a different model name. For example, I wanted to do neural net, I put in NNNet. I wanted to do CART, I put in RPART. That's the good part. The bad part is it will run these models whether you know what you're doing or not. So in particular, for the educational aspirations, there were 8 categories, but very few people were on the low end where they said they barely wanted to finish high school. More of them were on the high end where they said they wanted to go to college. So if 60% of my sample says they want to go to college, even if I just randomly assign people, or if I were to just say everyone wants to go to college, my accuracy will be 60%. So it'll look really good, but it doesn't really tell us anything that we need for merging this data onto the synthetic population. So in our code, we just made sure, because we knew that we had unbalanced categories, we looked at the log loss function instead of just looking at pure accuracy. And again, I'm not going to get too much into the weeds of this because it was more of a proof of concept to show that we could take this data. We ran these models, clustered them, got results, and used that for modeling onto the synthetic population. Ideally, if we had more time, we would have identified better variables and used those to train the model instead. So here we have the output for the k-nearest neighbors, which is the model we ended up using. Again, Carrot, very easy to use. It shows the k-max, which in other settings we would have taken much more time to decide on the values, but we trained that model locally using the HSLS data. So we had 7,500 cases. We took 5,000 of them to train a model. We validated it on 2,500 of them. And then once we had that trained, cross-validated model, we saved that and then brought it into the Azure Databricks cloud, because again, we were only working with 7,500 cases when we were doing the machine learning training, but the actual synthetic population of 9.3 million, when we subsetted it to 14 to 18, we ended up with 6.5 million, I want to say.
Oh, it was like 607,000.
Oh, sorry, 607,000. Still too many for my computer. So, but the process of training that model inside of R on my computer and then porting it to the larger Databricks platform, extremely easy.
So the next fun part was trying to map all this, and like many other groups will probably be able to tell you, as well, we had to keep trying over and over again because the first thing we did wouldn't work, and then the second thing we did wouldn't work, and the third thing. So, so we were using Azure Databricks and primarily relying on R. And so to get to this next part where we were using, GIS, required packages that weren't working very well or at all in Azure Databricks. So we needed to find alternative methods. Becca tried a package that you mentioned later, like relied on Java, which we couldn't get working, and so we ended up using Python and the GeoPandas package specifically. And so basically, this chunk of code is just part of what we ran as an example to map out all the colleges in North Carolina. So here's what we ended up with when we ran all that code, which allows basically for 6 categories. For those of you familiar with iPads, we're using sectors 1 through 6, where it separates public, private, and for-profit 2 years, and public, private, and for-profit 4 years. So even just from eyeballing it, you can see like there's a lot of underserved areas in Eastern North Carolina, for example. But so from there, we took this variable that we had predicted in the synthetic population, the preference to remain close to home, and that variable had basically 3 characteristics, 3 categories. Either they, had a very strong preference, somewhat strong preference, or like no preference at all. Like they had no preference to live close to home. And so when we took that synthetic population and just plotted out those who said they very much preferred to live close to home, we ended up with something like this, which I don't have a comparison to show you of the full synthetic population, but it actually looks very similar to this. So it didn't seem like there was a geographic differentiation, right? There's not like a big pockets of the state where like they don't care at all, and big pockets where they care very much, which is an interesting finding in and of itself. But more interesting is when we start looking at whether those students who want to live close to home actually have options available to them, right? Within a reasonable distance. So so that some of the average distances for students from their nearest college options was like for all colleges probably around like 11 miles on average, so like not very far. And for 4 years only, it was something like 18 miles, like not very far. But the maximum value, so like the students in the synthetic population who were the farthest from the nearest college option, when we're looking at 2 years, I think it was like 60 miles, and for 4 years, only was like 81 miles. So these students were pretty far from the nearest options. This map shows, essentially it's like a heat map of the distance from the nearest college for 2 and 4 years. So the vast majority of the state actually seems pretty well covered, right? Like the vast majority have, at the very least, like a for-profit 2-year nearby, which, this is a pretty conservative estimate. If we subset it just to, state colleges or state 2 years or whatever, this map would look a lot different. But other than the eastern side of the state, like everyone else seems to have within 10 to 15 miles. The different picture looks when we subset it down to just those distances from a 4-year college. As you can see, there's a lot more red and orange in this map, which tells us that there are some sections of the state where students want to live close to home and don't have a lot of options nearby them. Cool.
So as we've talked about, we've done a lot of merging and modeling. We're using a lot of different techniques. But one of the things that has come up a couple of times is that we were limited by the predictive variables that we could put into the model. Because no matter what data set you're bringing it from, you need to be able to find that variable in the synthetic population data and be able to model that. And so that was one way that the model has a limitation. Second, this is a proof of concept model, and so we don't have the most precisely measured variables here that we could have, and that's something that in the future that we really want to look for, and that we want to more accurately model all of this. And then we also use unweighted clustering, and so we know that with a complex sampling design that it's really important to get your weights right. So that's also something that we know that we need to do in the future, but given what I just think the maps are so cool. Given what we were able to do with the modeling and the merging that we did, like that's kind of where we had to stop in order to present. Next, lessons learned. First, we really learned that we need to start with the right stuff, meaning that when you are beginning with variables that are imprecise and that are not exactly measuring what you want to measure, you're not going to get the predictive power that you want out of your model. And so that's something that we really want to do to improve the model and to improve the predictive accuracy. Second, anytime if you all get to work with the synthetic population data, which I think is kind of a rare opportunity, just be careful because as we were talking, we were merging and we were modeling, and at times as we were talking to each other and talking within the group, as I say, like both of them start with M, but you're doing very different things, and so we were sometimes getting conceptually messed up as we were thinking about modeling data versus merging data, because we merged so much together, and it was so dependent on the synthetic population data modeling it correctly within that to get accurate models or accurate predictions, that sometimes we had to make sure that we were conceptually on board, not just methodologically on board. And then last, we talked a little bit about this, but we learned that there are system dependencies, and sometimes those broke down. So we were working in Azure, which helped us be able to work with large data sets and the cluster functionality. Well, Azure pulls from CRAN, which allows you to pull in R packages, and some of those R packages use JavaScript, but Java does not work in Azure. And so there's a big package called Google Way that I really wanted to use. It had all the functionality that we need, but we kept on trying to run it. I was like, why is this not working? And so then I looked kind of in the weeds of the coding, and it was using JavaScript. And then we found out it doesn't work with Azure. So it was just kind of just one of those learning lessons that as you're integrating more systems, that not all of those systems, if one of those dependencies breaks, then the whole cycle can break. And so we just have to, it's just one of the things to think about as we integrate, as we have more systems that are integrated into each other, which ones are going to be able to work together, especially with something that's open source like R, which has amazing capabilities, but does have some limitations. Last, applications and next steps. We do know that we want to improve the accuracy of the model. This was something that we did on limited time, and we were happy with what we were able to do, but we definitely want to explore weights. We want to add more pertinent variables. Those are two big things that we think will really improve the applicability of it. Also, this is an ideal situation, but we don't think it's very realistic, but we'd love to be able to merge it with the HSLS restricted data because that would be able to help us match much more and get much more less noisy estimates. So, and then last, there are like a next steps. This is a really policy relevant issue when you're thinking about doing high school counseling and also when you're thinking about community outreach initiatives. Just me personally, I had a student from Appalachia in undergrad, and she told me about coming from her community in Appalachia and how difficult it was for her to leave Appalachia and come to UNC. And so just from anecdotal experience and also the data that we have encountered, that we believe this is a really important issue to follow up with for high school students, especially as we've seen in the eastern part of North Carolina and in these kind of education deserts. Okay. Any questions?
This thing? Okay, cool. I think this is a really cool project. Really love the visualization with the map. I'm just wondering about with the heat map thing, you can see that in the borders of North Carolina, there are a lot of red spots, right? But I'm just wondering if you sort of expand a little bit, if you look at, for example, in the north or to the west, probably those people can also go to colleges in nearby states, so they don't have to find distance between colleges in North Carolina, right? So I'm just wondering, maybe moving forward, you will probably have some ideas to think about how to model that, right?
Yeah, that was one of the limitations that we talked about, the fact that our data kind of ended in North Carolina. Thankfully, North Carolina is amazing, so I'm not sure if they really need to hop the border. But a more practical consideration was the fact that in-state tuition. So if you are in one of these areas that are in the corner of the state, especially for North Carolina, the Northeast, in Western North Carolina, average income is a little bit lower, and state tuition is a little bit lower as well. So ideally, we'll find solutions that those populations can work with rather than assuming that they would be able to hop the border. But yes, definitely in any model, you would want to include those border colleges as well.
Hello? Okay, good. So my question is, you guys are sort of, at least it seems to me, that working off the assumption that distance and location of home is a major student concern when choosing college. I am wondering, though, if there's like future considerations to actually probe that. Because like there are a lot of other things that come into decisions, and like as Nestor mentioned, yeah, there's for-profit two-year schools nearby to a student, but what is the likelihood that a student from a college would actually be considering that option and moving forward with that?
Yeah, it's a good question. So there actually is quite a bit of literature out there about the role that proximity to colleges plays on not just whether or not you attend college, but also where you choose to go. So there's, I'm not going to dive too much into the literature itself, but we do know that there are differences between different like racial and ethnic groups, different like cultural groups. It depends somewhat on if your parents went to college or not. There are different characteristics wherein someone might be what you would describe as more distance elastic, like borrowing from like the term elasticity from economics, right? Where some students are more sensitive to distances from colleges than others. And so for a study like this that we want to be like as optimized or as effective as possible, you would account for those student differences. Part of the trouble with using things like the synthetic population with HSLS, for example, is that some of those characteristics end up in the models that we're predicting, right? But not all of them, because not all the variables will be in both. So yeah, I mean, so there's some work out there that already looks at that, but that's a good question.
Hi, that was very interesting. As a next step too is breaking it out by sector, right? Because that community college students are very different than four-year colleges, and that might show some of the patterns that he was talking about. But it's fantastic for what you were able to do in the short amount of time that you had.
All right, thanks so much, team. Great work. Round of applause.
And really quickly, sorry, unsolicited plug for the program. It's been amazing working with this team and everyone in particular. It's been an amazing opportunity. And I know Nestor wouldn't have mentioned it himself, but when we were going through the R problems, he essentially learned Python in 8 hours and created all the maps that you saw. So I think that's just really a testament to what you can do when you're around people that are really interested in your work and you have the ability to and the time to pick up those skills. Thank you.